Hi and welcome to my Essay 1 of Exam 3 video. Today we're going to be talking about a lot of things when it comes to the heart. We're going to talk about two different tissues that we find within the heart, one that contracts just like skeletal muscle, and then another one that actually initiates contraction. So let's go ahead and jump into it. So we mentioned there were two types of tissue that we're going to talk about today. Those are the autorhythmic cells. They're also known as pacemaker cells. They're found in what is known as the SA node and the AV node and a couple other places within the heart. And then there's also contractile cells, which are basically like muscle cells but specific to the heart. They're also called myocytes. Myo meaning muscle, cyte meaning cell. So cardiomyocytes. So let's go ahead and start with the pacemaker cells because those are a little bit simpler to talk about when it comes to how they work, what they do, and so on. So I'm going to draw some pictures here for us. We love pictures in physiology. I'm going to draw my pacemaker cells as kind of an oval shape like that. I'm going to draw it right next to what we'll call a myocyte, cardiomyocyte, and let's draw it into a square. This is not an actual representation of what they look like. I just draw them in different shapes so that we can kind of get an idea of which type of cell we're talking about. Now you'll notice that I drew the cells right next to each other. The heart is a very special organ where we're going to have muscles that are basically attached really tightly to each other. The cells are really closely bound to one another, and that's because unlike skeletal muscle, cardiac muscle is not attached to any bone. So when it contracts, the only thing it has to contract on is itself. And so that tightly bound space between the cells is what gives it the ability to really create a strong contraction when it's not really connected to anything but itself. Now, something that's really important is what we call a gap junction. Gap junction is exactly what it sounds like. It's a gap between the cells, and it's not just between pacemaker cells and cardiomyocytes, it's also between cardiomyocytes and other cardiomyocytes. It's also between pacemaker cells and other pacemaker cells. All cells have kind of this highway system between them in the heart that allows for action potentials to propagate or to spread through the heart very quickly. As you might have noticed, your heart is a very important part of your body. You can't really live without it. And it's really important that it contracts in unison with one another, with all the cells working together. Because if we have random contractions, then we're going to have something called death, which is not what we want. So let's get back into what we were talking about before, our pacemaker cells. So these gap junctions allow for action potential to propagate or to travel from cell to cell. Now, how do action potentials work? Well, they're a little bit different in the heart than they are in most other parts of the body. In our pacemaker cells, they have the ability to, quote unquote, randomly depolarize and begin an action potential. It's not necessarily random because they do this at a certain rate, at a certain pace, hence the word pacemaker cell. Now, one really important thing to note is what is known as an HCN channel. So that's an H as in Harry Potter, C as in cat, and N as in nucleotide. So HCN, it actually stands for hyperpolarizing cyclic nucleotide, because this particular channel is capped with a nucleotide, and which is provided by our CAMP, which is made by adenyl cyclase, which is found in another part of the same cell. So this one channel is responsible for what is known as the graded potential of our autorhythmic or pacemaker cell, which is essentially the very beginning part of the cell depolarizing. But what's really interesting is this cell, or not this cell, this channel, excuse me, will open up like that, leaving some space, and will allow sodium into the cell. Now you'll notice that this is a little bit different than what we usually do, because when our heart does not necessarily have a constant resting membrane potential. The heart cells are in constant, what I would call, flux or flow of electricity and charge. And that's highly due to this channel. So this channel, when the cell is going hyperpolar, when it's decreasing or becoming increasingly negative within its membrane, that's when this channel opens. And that allows the sodium to come in, and that actually begins the opposite of hyperpolarizing. It begins to repolarize, or not repolarize, begins to become more positive. As you see here, sodium is a positive charge of +1, and so as we get more sodium coming in, the more positive it becomes, but it initiates when the cell becomes more negative. So it's a little bit funny, which is why it's been nicknamed as the funny channel, because they're like, huh, that's funny. When it gets hyperpolarized, it actually initiates the thing that repolarizes the entire cell. So what does sodium do once it's inside of the cell? Well, you might think, and it would make sense, that the positive charge from our sodium would propagate through our gap junction and begin our contraction in the myocyte. But that's not what happens. There's a couple of steps in between. Sodium builds up a positive charge inside of our cell. This positive charge will open another channel. This other channel is going to be a calcium, voltage-gated calcium channel. Right there. So we'll have extracellular calcium rushing into the cell once this channel is open. How is this channel open? Well, it's voltage gated, which means it's sensitive to change in electricity or change in charge. That charge from the positive sodium ion is what initiates the opening of these channels. As we get calcium coming into our pacemaker cell, calcium, just like skeletal muscle, calcium is essential for contraction within our cardio muscle. But in our skeletal muscle, we don't have any extracellular calcium coming into the cell to initiate that contraction. If you want to learn more about how that works, you can go back to one of my earlier videos, and I talked about that pretty in depth. But back to here. So we have calcium coming in. Now you might think, all right, calcium, that's what initiates the charge that goes across our gap junction that basically spreads this depolarization and the action potential. But we're not quite there yet. There's still something that we have to do before we get to that point. So this calcium actually binds to a familiar channel that I've talked about in one of my past videos, known as the RYR. Now you notice I drew it right in the middle of the cell, and that's because the RYR is actually found in what is known as the SR, or the sarcoplasmic reticulum. The sarcoplasmic reticulum, just like in skeletal muscle, is responsible for the storage of all the cell's calcium. And calcium, as we've already noted, is essential for contraction. So, first, just to recap, we have our hyperpolarizing cyclic nucleotide channel, which opens up once the cell potential gets to a more negative number. When it opens up, it allows a positive charge, sodium ions, to rush in, which then initiates the opening of our voltage-gated calcium ions. Our calcium comes in, and it binds to our RYR. Now remember, our RYR channels are ligand-gated, which means they have to have a particle that attaches to the channel, which opens it up, available making our sarcoplasmic reticulum calcium available to rush out into the rest of the cell. Now, once that happens, now we get to the point where we have a big positive charge that is going to propagate or travel through our gap junction into our cardiomyocyte. Once we get that to happen, then we're going to have a cascade of events that happen to create a secondary action potential in our cardiomyocyte, and that then creates or initiates contraction, and it spreads throughout the entire heart. And this happens very, very quickly, and that's why we're able to have heartbeats that are like 60 to 120, maybe even higher beats per minute. Now, that is how the pacemaker cell works. Pacemaker cells kind of have their own rhythm. That's why another word for pacemaker cell is autorhythmic cells. Auto meaning self, rhythmic is rhythm. So they have kind of like their own rhythm that they always follow. Now, in order to understand more about that, I'm going to go over some basic anatomy for the heart. Because pacemaker cells are only found in certain tissues or certain spots in the heart. So I'm going to draw a very basic heart. In fact, it is not anatomically correct, but we'll go over something. We're all familiar with the heart symbol. I could actually draw out a real heart, but it would take a lot longer, and I don't want this video to go as long as last week did. So we have essentially 4 main parts to our heart. The top 2 are known as atriums. The bottom 2 are known as our ventricles. Basically, we have our veins drain into the right atrium. Then we go through what is known as the tricuspid valve into our right ventricle. Then we go through what is known as our pulmonary semilunar valve. And we go into some arteries that go to our lungs. Our lungs have the oxygen that we breathe in, which oxygenates the blood. The blood comes back and drains into the left atrium. The left atrium goes through our bicuspid valve into the left ventricle. The left ventricle squeezes the blood into the aortic semilunar valve, which pushes blood into our arteries and throughout the rest of our body. That's the very basics of how our heart works. Now, in order to get a better idea of what what our pacemaker cells do and why they work the way they do, let's point out where they're located in the heart. So I'm going to clear this up a bit so it's not so confusing to look at. So we have in our right atrium, we have the spot right here. That's kind of up in the upper, to you would be upper left corner, but from the heart's perspective, it's the upper right corner. We call this our SA node. And it's just a spot in the heart that is very densely packed with those pacemaker cells, the autorhythmic cells, that have their own rhythm where they depolarize and they go through an action potential, sending out those positive charges to initiate action potentials throughout the rest of the heart. So that starts here in the SA node, and it goes about 60 depolarizations per minute, so 60 times per minute, give or take. Obviously, this is a very generalized example. Then we have what is known as the AV node. It's kind of down here. It's still in the right atrium, but it's closer to the center of the heart. And so when we have our positive charge go through, it's going to start at the SA node because the AV node only goes slower than the SA node. It goes probably 40 times per minute. So our SA node is most commonly the one that initiates the depolarization, and then by connection, then the contraction happens. But our charge will go in all directions like this at first. So I have arrows pointing from our SA node, and they kind of go in a diagonal direction, and they end up, our depolarization ends right here at around the AV node. The AV node then has two sets of branches that go down. One goes down on the side with the left ventricle, and one goes down on the side with the right ventricle. And these two branches are full of those pacemaker or autorhythmic cells. So when we have, here I'll draw the arrows in a separate color so it's easier to see. But when we have depolarization occurring, starting with our SA node, it goes from one patch of pacemaker cells to another patch of pacemaker cells. And so it kind of goes in that general direction and fills up both atriums, and then ends right here with the AV node. And then it goes down the branches that they're connected to, and from there spreads out in all directions. Now remember, I'm still talking about the action potentials, or the cells depolarizing and becoming more positive. You see how that works? It starts up here, kind of goes through all both atrium, and then from there goes down the branches, and then from the branches spreads out throughout the rest of the ventricles. And because our left ventricle is the one that's pumping that blood into our arteries and throughout the rest of our bodies, that's a lot of work. So usually our left ventricle is a little bit thicker because it has to have a little bit more muscle to give some more power to that contraction, so we have our heart can be strong enough to pump our blood back into our body. So it's usually a little bit thicker like that, which means that our left ventricle is usually the last part that gets the depolarization message, because it has to go through all that tissue to get to the very end of this thicker muscle tissue, this thicker cardiac muscle tissue. So if we wanted to draw kind of like a really long arrow that tells us the story or the path that our depolarization takes place, it'll look something more like this. So if we're just going to summarize all those arrows that I drew into one big windy arrow, it would look more like this. Starting at the SA node, going down to the AV node, going down branches, going all the way through the ventricles, and we're ending at the very top left part of our left ventricle, just like that. And then how it has to depolarize, because we don't want our heart to stay contracted. We don't want it to stay squeezed shut, because otherwise it wouldn't be able to allow any more blood back in, and we would pass out and die. So then it has to depolarize to allow those muscles to relax again, allow more blood to come back into the heart before contracting and squeezing it back into the rest of the body again. So when we depolarize, it's very similar to the path that we just took, but just kind of like flip all the arrows. It just goes backwards from what we just did. And that's kind of how that works. Now, we have some really cool machines in our healthcare today. One really important one is called an ECG machine. ECG machines, they kind of sense, or they're able to tell us this story of how our depolarization or our action potentials are going in our heart. What I just described is what we would expect to see on a normal, healthy individual who has a good beating heart. Now, if someone were to be having like a heart attack, then we would not see this pathway. But I'm getting a little bit ahead of myself, so I need to kind of explain to you guys, before we get to that point, how an ECG works. And I'm going to try and make it as simple as possible so that we can get a general understanding of how this works in a short amount of time. So let's imagine for a moment that our heart is only made up of 4 cells. I'm totally making this up. This is not true at all. But this is just going to be an example that will help us understand how ECG machines work. Okay? Those 4 boxes are our 4 cells, right? Now when we have a depolarization, depolarize meaning our cell has a resting membrane potential or a negative potential of around negative 90 in cardiac cells. That's negative 90 millivolts, by the way, in case you're wondering. So negative 90 millivolts. So it's a pretty negatively charged tissue. So we have lots of negative charges. I'm going to drop a few negative charges in all of these cells. And those negative charges are maintained by sodium, potassium, ATPase pumps. And if you're wondering about what those are, I talked about those in one of my first videos that I ever made. Go back and watch it, or watch somebody else because they did a better job probably. Anyway, so we have this negative charge inside of our cells. Now, because charge can't necessarily be created out of nothing and it can't be destroyed, we have what is known as just a separation of charge. Everyone knows opposites attract, right? We have positive and negatives, and they love to stick to each other. So if we separate them, we're going to see wherever there's an isolated negative charge, for every one of those ones, we're going to see an isolated positive charge that will be just outside of the cell, really close to the membrane, because it's like having a piece of paper with a magnet on both sides. They're going to want to stick to each other through the paper, but the paper is keeping them from touching completely. That's sort of the analogy that I like to think of when it comes to this. So I'm going to draw a lot of positive charges outside of all of these cells. So this is what the heart would look like when it's at rest, when it's not contracting, there's no action potential going on. These are just cardiac myocytes minding their own business. And when we have an ECG machine, we have kind of 4 quadrants that we want to put these some sensors that sense electrical charge on. And the really big one that we like to look at most is having this negative charge up near the right ventricle and this positive charge right near the bottom of the left, or the left, sorry, I said right ventricle, I meant right atrium. And then this positive charge down here right near the left ventricle, near the apex of the heart. So it kind of goes like a seatbelt, like a diagonal line down across. So when we have our ECG machine, this is a sensor that senses negative charge, and this is a sensor that senses positive charge. You notice there's going to be some charges here for us to see on a graph. The ECG machine will take the data that it gets from what it's reading from the heart, and it'll put it on the graph. So let's draw a graph real quick, just like that. So on the y-axis, we're going to have charge. On the x-axis, we're going to have time. Okay? Now, we can say that, let's say, the heart at rest is right there. So that's our beginning start line. That's at negative 90 millivolts. When we have an action potential starting from our SA node, it's going to propagate, or it's going to travel down this general direction. So we're going to have that depolarization traveling down. Now, depolarization, remember, that calcium rushing into the cell to connect to the troponin, which is on top of the tropomyosin, which falls off the actin chain, and we're able to get the myosin head attached to the actin, and it does the power stroke when it has the ATP hydrolysis, and so forth. I went over that in my last video, I think, but you can go back and watch that. So, basically, we have positive charge entering the cell, hence depolarization, undoing our polarization. So positive charges will begin to rush into our cells. So these are becoming positive. And because every time we see an isolated charge, we're going to see its opposite charge just outside of where it's at, right? So we're going to have those positive charges inside of the cell. For every one of those positive charges inside of the cell, we're going to find a new negative charge just outside of the cell. Like that. And this goes down the line. This happens to all the cells, starting from the one that's closest to the SA node all the way down until we get to here towards the bottom or apex of the heart. And so as we're doing this, what we're doing is we're creating a direction of our charge being changed. Now notice we're having negative charges traveling down towards our positive sensor. When we have a negative charge traveling towards its opposite sensor, negative charge towards the positive sensor, then on the graph that's read by the ECG machine, we're going to see it go up. That's the graph reading this action potential traveling down towards our positive sensor. And this happens if we were to say, we flip our sensor, say we made a oopsie, and instead of having our negative sensor up here and our positive sensor down here, we accidentally flipped them and put them in the opposite places. So say this one's negative and this one's positive. Now we still have our negative action potential propagating down towards the apex of the heart. But instead of that negative charge traveling towards a positive sensor, now that negative charge is traveling towards a negative sensor. And instead of seeing this wave go up, we're going to see the same magnitude of wave, but it's going to go down, so in the opposite direction, like that. And that's essentially how the ECG works. Now that we have that basic idea of how ECG machines work and how they read action potentials inside of our heart, let's go over the normal path of what we would see in a healthy individual in the heart. We kind of went through how action potentials travel through the heart, but now let's see what we would see on an ECG machine if our patient was a healthy individual who had a normal working heart. So, I'm going to draw a couple hearts here. Just try and stay with me. We're going to go through a series here. So, first heart. Where does our action potential start? SA node, right? Travels down towards our AV node. Both atriums depolarize. So depolarization, meaning we are sensing with the ECG machine the charges that are outside of the cell, not the charges that are inside of the cell. So depolarization, positive charge goes into the cell, negative charge is outside of the cell. So we have negative charge basically going towards our AV node. That general direction happens to be going towards our positive sensor. Negative charge, positive sensor, we see a wave go up. That's what we call our P wave, right? Now, we know what happens next. Going from our AV node, we go down into the branches. Now, because of the way the heart is shaped, we're going to have the positive or that negative charge coming out from the branches towards the rest of the ventricle. The general direction is actually going to be closer to pointing towards our negative sensor in this case, because we're coming out of the branches and propagating into the rest of the ventricles. So we'll have a general direction of going back up, kind of in this similar direction of our negative sensor, and we have a decrease because that's negative charge going towards a negative sensor. So we're going to see a dip in our graph. So it goes below where we started, just like that. And that's what we call our Q wave. Once we have our ventricles are starting to fill out more, we have more charge going down than to the side, and that will be more towards our positive sensor, and that's what we call our R wave. So it goes up because it's going negative charge to a positive sensor. We're going to see our R wave go up, and then just like we talked about last time, when we have a path of depolarization, the last spot that gets filled up is going to be the upper left ventricle, that very upper left hand side. And so we're going to have it more towards our negative sensor. So negative charge going up kind of towards our negative sensor. They're the same. So sign, right? Negative to a negative. So we're going to see it go down again. So it goes really high up, goes really low down, like that. And then our heart is fully contracted. So what happens after your heart is fully contracted? Well, it needs to relax again, right? It needs to depolarize, allow those muscles time to relax so that we have blood flow back into the heart. And so, just like I said last time, we have those arrows go in the same path but opposite direction when we're depolarizing. So we're going to have our first, and since we're depolarizing, we have positive charge going back into the cell, or sorry, we're depolar. Did I already say depolarizing? Basically, we have negative charge that goes back into the cell. That's right. We're repolarizing. That's the correct word. Sorry. We're repolarizing, having negative charge go back into the cell, leaving positive charge just outside of the cell, just how we were when we started. So we're going to have our positive tail this time going down and around, up, in the same direction that we came, starting from the SA node, but this time we're starting from the upper left ventricle, and it just goes the opposite way. Our positive charge will go back with our last part of our heart that relaxes, that repolarizes. It's going to be the SA node. And so since we have a positive tail, and it'll be going towards our negative sensor, we're going to see a little bump go up in our graph again. Like that. And that is what we should expect to see if a patient is healthy and their heart is working properly. On an ECG machine, that's like the general, I drew it very poorly, but that's the general graph that we should see. Little bump, P wave, little divot called the Q wave, really high spike called the R wave, really low spike called the S wave, and then the little bump, the T wave. And that's how an ECG machine works, and that's how we're able to tell, or how doctors are able to tell if there is a problem with your heart. All right. So I didn't really go over how cardio myocytes work as far as how those action potentials work. I just told you how the autorhythmic initiates its action potential. So let's go back real quick. After talking all about action potential, let's go back and figure out how our cardiac muscle cells or myocytes work. So I'm going to still draw them with a square just because I like to keep it simple in my mind, or as simple as I can. And there's going to be a couple different channels that are important to note when it comes to our cardiomyocytes. The first one that I'll talk about is just a normal voltage-gated sodium channel. Now notice I didn't talk about voltage-gated sodium channels when I was talking about autorhythmic cells or pacemaker cells because they don't have any. But our cardiac muscle cells do have voltage-gated sodium channels, which is something that you see on pretty much all the other cells in the body. So you should be pretty familiar with this by now if you've been kind of going through my videos. So we have voltage-gated sodium channel, and we also have voltage-gated calcium channel, also known as L-type. So I'll just do L calcium for that. L-type calcium channels, which is a little bit different than what we'll see in skeletal muscle. Then we have several channels dedicated to potassium. And they're all slightly different, which makes them so much fun to memorize. So we have potassium, or KUR channel. We have KU channel and KR channel. And then we also, in addition to that, we have potassium leak channels, which are always open, making potassium extremely permeable to our cardiomyocytes, which is part of the reason why our resting membrane potential of our cardiomyocytes is so low. If you remember from earlier, one of my earlier videos, I talked about neurons. Their resting membrane potential is around -70. A lot of cells in our body don't go much lower than that, but in our heart, we go all the way down to -90, which is quite negative. And the biggest reason for that is because we have all of these different potassium channels that act a little bit differently, but what it does is it allows potassium to really go through our membrane really easily. So we get a lot of potassium kind of just leaking out, and since potassium is a positive charge, every time we have one potassium leak out, it leaves a negative charge behind, which is why it's so negative in there. So, cardiomyocytes have really cool features. One of my favorite things about them is they act very similar to skeletal muscle. So they'll, just like skeletal muscle, they have an SR, sarcoplasmic reticulum. Inside of the SR, we have that channel that kind of goes across that SR membrane. We call it the RYR, same as we saw in the pacemaker cells. Very similar to how we saw in the pacemaker cells, we're going to have our, first that gap junction, right? That connects us to our pacemaker cell. And that pacemaker cell will send in, when it goes through its action potential, it'll send in its positive charge. That positive charge is going to open up our voltage-gated sodium channel. Our voltage-gated sodium channel is going to allow sodium to rush in, and our sodium channel will then increase that positive charge so much so that it will open up this L-calcium. Now, you might have noticed that this L-calcium channel took a while to just open up like that. It is voltage sensitive, but It's called L-type because L stands for long, as in it takes a long time to open. It takes a while to get it moving. But once it is open, we have that calcium rush in, and just like we saw in the autorhythmic cells, that calcium connects as a ligand to our RYR channel that's on our SR, and that opens the RYR channel, which allows even more calcium to rush out of our sarcoplasmic reticulum into the rest of the cell, and it initiates contraction. And from there on, it's the exact same as if the cell were a skeletal muscle cell. So if you want to know more about how that contraction works and how that cycle happens, you can go back to my last week's video where I talk about that in depth. Now, some very, very cool features here is skeletal muscle. We can initiate contraction and then let it to begin to relax, but before it's fully relaxed, we can send in another action potential to get it to contract again. So we can kind of have this increased strength of contraction. Well, with our heart, we don't have that because you don't want an increased strength of contraction. You don't want to reach tetanus or constant contraction with your heart, because we need both the contraction and the relaxation are vital to the functions of the heart. And that's where all of these potassium channels come in. When we have our calcium rushing in, and then even more calcium from the SR is rushing into the rest of the cell, it's a ton of positive charge. If we were to chart our membrane potential, just ignore the cell for a second. I'm just going to make a chart right there. The y-axis is voltage or membrane potential, and then the x-axis is time throughout our action potential. Right, so we're starting way low, -90. We go up. Our propagation from action potential through the gap junction from the autorhythmic cell initiates opening up that sodium channel. That sodium channel is going to spike up our membrane potential, so it's in the positive now, and then it will begin to go down. Once it reaches a certain positive number, that voltage-gated sodium channel is going to close itself, and so it won't allow more sodium than is necessary into the cell to begin this action potential. And then our calcium is still going to be present within the rest of our cell. And that's a lot of positive charge, because for every single one calcium, we get 2 positive charges, because one calcium ion has a positive charge of +2. And then we have these potassium leak channels that begin to open, not the leak channels, sorry. Potassium KUR, KU, and KR begin to open, allowing potassium to leak out. And potassium, 3 potassium going out of the cell, is only a net -1 when it comes to charge, because we have 2 plus positive calcium ion coming into the cell and 3 plus potassium ions leaving the cell, essentially saying we have add -3 to the inside of the cell. But because we have these 2 gradients kind of fighting each other, it takes much longer for our cardial myocytes to reach back down to a normal resting membrane potential. And so we have what is known as a plateau phase. This plateau phase kind of drags on until enough potassium is leaving that it kind of overcomes the amount of calcium that has come into the cell. And then we'll see it go back down and repolarize to where we see our normal -90. And that's kind of the pathway of how action potentials work within our own cardiomyocytes. So we have initiate, starting from a propagated action potential from our pacemaker cell through our gap junction, opening up sodium channel. Sodium opens up, becomes more positive. We open up our L-type, long calcium, so it takes a little bit longer to open up. But once it does, all that calcium rushes in, then it binds to the RYR and the sarcoplasmic reticulum, which releases even more calcium becoming very, very positive. But when it reaches that very, very positive point, our sodium voltage-gated channel closes itself, and these potassium channels begin to open. The entire time, throughout this entire process, the potassium leaks channels are always going to remain open. So there's always some potassium that is leaving the cell, but because of the magnitude of positive charge that we see with the calcium being released into the cell, we don't really see its effect very much until we get down to this point. And then finally, we have calcium gradient fighting with the potassium gradient, creating the plateau phase. Finally, potassium opens up enough of these channels so that it overcomes the calcium positive charge. We get calcium starting to be pumped back into the SR, and then we also get potassium pump that pumps calcium back into the extracellular space, and then we get back down to our very negative resting membrane potential of negative 90 millivolts. And that, my friends, is the heart. If you have any questions, leave a comment. Any concerns, leave a comment. Feel free to not like and subscribe. I'm okay with not being famous.